All right, well, we're going to get started here. There's a couple more people trickling in. But anyway, hello. My name is Joe Giardino. I'm a senior development lead on Azure Storage. So we are going to get into all sorts of wonderful scenarios and things about Azure Storage specifically, but also kind of from the SharePoint perspective with some kind of unique scenarios, some of these hybrid scenarios, things like that. So quick agenda. We have a lot to cover today. So we have an introduction. We're going to go over Azure Storage, some of the key concepts. We're going to look at a little bit of code, the different abstractions that are available, blobs, tables, queues. We're going to have a larger emphasis on the blob size since it seems like it's most applicable to SharePoint developers. We're going to talk about some of the scale-out things. We've already noticed that some third-party people are starting to offer solutions that do some of this for you, put things in the cloud on your behalf, but it's still your storage account, so these are some things that are good to know. And then we're going to go through some of the best practices and kind of specifically some of the scenarios that SharePoint people may find interesting and compelling. A couple notes about the code. Since there's so many different scenarios, at the booth and Ask the Experts, I was talking to different people, and they were saying, how do I do media streaming? How do I, one guy was importing thousands of documents in TIFF format and wants to do OCR and all this other stuff. So there's a variety of scenarios. You can think about custom web parts. You can think about different document collections, all these different things. So we're not going to do a whole bunch of SharePoint-specific code, but we're going to focus on the storage side of it and then how you can kind of piece that together with your existing solution. We have something called analytics. We'll get to that. Again, kind of covering best practice from the storage perspective, and then kind of putting it all together, look at the high-level scenarios. And then we're going to try to save questions to the end. Hopefully, we should be about an hour, but we should have time for some Q&A at the end. So who am I? I already covered this. My email's there. I'll be down in front afterwards, and you can get a hold of me if you have more questions after there. There's my Twitter. I'm not the most popular Twitter out there. I've done just a couple based on Azure. And then more importantly, who are you? So I got this from the little My SBC portal, and we're trying to tailor the message to who's here. And the majority of you are developers or IT pros with a few business decision makers. So we have some content for kind of all of you. For the business decision maker side, we're going to cover things like cost and some of the scenarios, why you would want to do this, what makes it compelling. But for the developer and IT pro, we're going to talk about some of the key things that would enable you to successfully deploy this hybrid scenario, and then, again, go through some specific code, best practice, and the like. All right, so let's get started. Azure Storage. First of all, something that I was hearing a little bit on the floor was, what is Windows Azure? So let's just start at the high level. And Azure, very simply, is Windows in the cloud. It's the platform that Microsoft has designed and runs on your behalf in our data centers for you. And there's a whole bunch of different services, an entire menu of different things you can use. However, they've been put together for sort of three kind of conceptual ideas. And again, this may seem familiar to some of the developer crowd in the room, but we have software as a service, which basically is kind of like O365. If you go to the Azure Marketplace, there's things like Umbraco and WordPress and things like that. So software that's already built for you that you can just easily deploy. Then we have infrastructure as a service, and this has kind of made a big splash here, where now I can take an existing deployment, a virtual hard drive, or basically an on-prem app they already have, and just upload it to the cloud, and then use our self-healing fabric, the SLA that backs the uptime, the availability, and things like that. Leverage all of that. This really helps with A, migration, and B, also some of these bursting scenarios, right? So I don't have to pre-plan and pay for all this hardware up front. I can just pay for or use what I need, and then when it comes to Christmas time or whatever your peak load, I can just burst seamlessly into the cloud. And then lastly, we have this thing called Platform as a Service, and this is where you are basically writing your application to know that it's in the cloud. You're going to take advantage of cloud storage, maybe SQL Azure, all these different services that we offer to make this kind of compelling scenario. And if you do this, you can make a truly scalable app. So we'll kind of talk about who's using it and how they do that. But when we talk about scale, we're not talking about gigabytes. We're talking about terabytes, petabytes, all the way up. So anyway, so we have services for multiple models. And the key thing is it's rock solid. It's always on. You have, by migrating to the cloud, changed your last hard drive, done your last hardware refresh. All that's going to be done for you. Another thing that people are asking about is specifically around data. A lot of people are managing solutions for third parties, and they say, okay, my data can't go outside this geography, or it can't do I can't store it in a solution that's not, for example, HIPAA compliant or whatever. So these are the existing ones we have based on the different services. There's a lot of work in this area just to make sure that if compliance is the blocker, that we kind of take care of that. So there'll be more of this coming. There's some resources if you're curious online. You can get more details about this. All right, so Azure Storage for the SharePoint developer. Hybrid storage scenarios. So first of all, some of the key scenarios we were talking about, especially media, right? Uploading a 10 gigabyte movie that I want to stream to clients is great, but do I want to shove all of that in my SQL server and serve it straight out of there, right? My SQL server gets overloaded very quickly. It gets very big very quickly. And then also you have certain scalability things when 50,000 people try to watch it at the same time. Large media files are great there. Also document collection. Archiving is another great scenario. Basically, the cost of storage becomes very, very compelling compared to additional SQL instances, managing even ever larger and larger infrastructure. And some of the stuff we're going to talk about too, there's ways to kind of skip the entire trip up through the SharePoint server to the backend and just have users talk straight to storage in a safe and pre-authenticated way. So we'll get to that in a second. Again, there's some third-party providers already offering some of this today. The key thing for this crowd is if you're going to leverage some of that to understand that a storage account is a shared resource, what the scalability targets are, and that totally depends on how you structure your data, how people are going to access it. Again, one of the key benefits is reduce the size of your SharePoint DB, and also, additionally, the number of, the size of your farm and servers you have to deploy to serve all these large data. All right, so key abstractions. So when is there storage, blob, tables, queues? Blobs are what's going to be really key for this audience, but we'll go over all three. And you can literally think of blobs as files in the cloud. And we have two variants. One's a block blob, one's a page blob. A block blob is optimized towards streaming workloads and just kind of general purpose files. A page blob is optimized for random I/O, specifically virtual hard drives and the like. So a block blob, you can upload out of order. You can basically create a whole bunch of blocks in the cloud and then define a blob as being this block 1 through 10 in a row. That's now my blob, and I can download it. Page blob, you will go ahead and say this blob is a terabyte, and then start writing to it in 512-byte aligned chunks. And then, again, reading it not in 512 bytes, but whatever range you want. So we've built disks and drives, which is what IaaS basically runs on. So now you can mount a durable NTFS file share or a virtual hard drive in the cloud that's backed by page blob and made durable for you using blobs. Tables are a strongly consistent NoSQL structured store. A key part of all of these abstractions is that we use the same exact backend, the same durable file system for everything, so that you get a consistent developing experience across them, but also some of the ecosystem around it, like the analytics and the logging and the auto-scaling, is there in each of these abstractions. So tables is great because a blob, for instance, a single blob is what we call a partition. It's the unit of scale, and there's certain scalability targets around there. A single table, there's two key indices we'll get to, or properties, a partition key and a row key. And the unit of scale is just literally how much data shares the same partition key. And so if you structure data right, you can just expand terabytes all the way up. And then queues is a durable asynchronous messaging system. This is useful for guaranteed message delivery. Also, when you're making these scale applications to decouple different components, right? So now my producer doesn't have to have some sort of web service hook to this guy that's going to process all my images and do OCR and things like that. He just can put a message in a queue. These guys can read from the queue. And then there's kind of best practice about how to read and delete these messages so that if one of my roles falls over, I don't lose any data. All of this is exposed via open REST APIs. So pretty much any device that can make a web request can talk to storage. This is really, really convenient to be everywhere and to be open and embrace, pretty much every device. We understand that some people have iPhones and iPads and, Android tablets, things like that. We also know that everyone really loves writing REST. So for those of people that don't, we've provided some easy-to-use client libraries, right? And we've kind of baked in best practice to the first extent we can into these libraries. So for example, the .NET library or Java library, you can say, here's a stream, I want to upload it, and I'd love you to use 20 parallel connections. It'll manage that, schedule it for you, do everything you need to do, absorb faults or failures. So let's say I'm doing it over Wi-Fi or something like that, right? My connection's spotty. It will actually absorb those failures for you. You won't even know. It's one line of code. All right, so here's some of the characteristics. Azure Storage is a pay-for-what-you-use cloud storage system. What that means is there's no upfront cost. There's no sort of lock-in contract or thing that you have to commit to. Depending on your usage and depending on geo-replication and a couple other things, there's a price per gigabyte per month, and that's it. Bandwidth into the data center is free. Egress is what you pay for. There's a cost for transactions. It's just been reduced by 10 times, so for most people, this becomes an afterthought. I think it's a penny for 100,000 transactions now. But the key part of this is it's durable. So every single time you write something to storage, it's made durable on your behalf. We keep 3 copies for you of your data across what we call upgrade domains and fault domains. And what this means is if you were to think logically of a data center, right, you'd have multiple racks. Any single piece of hardware that could impact multiple servers is considered a fault domain. So you think of the router on top of a rack or the power supply or something like that. And then what we do is we cut across these, and we call them upgrade domains. So what this means now is your 3 copies of your data will be in a different fault and upgrade domain. So now what can happen is, let's say this router goes down or this server literally sets on fire. At the same time, an upgrade goes up, and this guy isn't available, or his network stack or something happened. We still have a 3rd copy, and within minutes, we'll spin up that 2nd and 3rd copy again to re-meet that quorum for you. So we're durable and we're available. On top of that, so this is the local replication side, we have something called geo-replications. So what we do is we build our data centers in pairs. Unlike some other cloud providers, what we do is we try to put the distance between those at 400 plus miles. So now when you have a major event like a hurricane or tsunami or whatever, and a data center physically does not exist anymore, right? We have a backup data center 400 miles away, and we've been asynchronously geo-replicating your data to that backup data center. So now, in the geo failover case, all we have to do is update DNS entries to point to the backup, and you're back up and running. Let's say that your business is dependent on its data, right? Without your data, you're not alive if you're Facebook or one of these vendors, these large companies. This is huge for your business because a lot of people, when they do on-prem, they think, okay, disaster recovery or something, I'll ship a tape drive to the other office once a week or things like this. With asynchronous geo copy, it's always happening. It's within minutes, and you're always up. So availability, we kind of talked this a little bit, but the key thing here is storage, you will get a financially backed SLA. So what that means is if for some reason something happened in the data center and we went below that SLA, you would get paid by Microsoft. So we are guaranteeing such and such an SLA, and these things keep improving over time. On top of that, we have designed our architecture to absorb these faults, to make sure that we're always up for you, and that you can depend on that, take a dependency on it. There's some different best practices about how to access things, and we'll get to that. And then lastly, scalable. So we're a cloud storage system, right? We're talking about data sets that could not easily be stored in any single computer a lot of the times. We're already at the size of petabytes. We've got very, very large customers. SkyDrive uses us, Xbox Live Music, things like that. And so everything is designed to scale out and in. And the key thing here is this is done automatically for you. And then the other thing is strong consistency. So what does this mean? Some other cloud providers offer a eventual consistent model. And what we think is it's best practice, it's easier for developers if they have strong consistency. So again, when we talked about those 3 copies, when you make a write to storage, we have made it durable, but we've also went to all 3 copies and committed the data in some durable form before we acknowledge back to you that we have it. And so now, immediately following that write, your data is made available to you. And that's what strong consistency is. In an eventual consistent model, immediately following that write, there's a chance you may get the previous edition of the data. And now it's up to you as the application model, or as the application developer, to handle this in your application and do a few backflips to make that work. So all of our data stores, these different abstractions we talk about, use a strong, consistent model. We think this simplifies development for you. So again, all abstractions are backed by the same store. The feature sets across use the same features: geo, durability, strong consistency, the auto scale, the monitoring. One of the key things behind this that's advantageous on a cost perspective is this allows us to blend different types of traffic. So on the back end, for example, a blob may be more I/O bound, whereas table may be more CPU bound. By using the same resources, we can blend that traffic and lower cost of the overall system. It's scalable. We'll look in a second about who's using it. These were some numbers we put up last June: 880,000 requests a second. 4+ trillion objects. It's growing, so I'm sure these numbers are out of date already. And there's great performance and a very low transactional cost. Again, the REST APIs and client libraries. So here's the pricing model for all the decision makers in the room. So there's a calculator on the bottom if you care. Price is anywhere from 12.5 to, it's actually 3.7 cents per gigabyte per month, depending on usage and redundancy. Generally speaking, local redundancy, where you disable geo-replication, is 27% cheaper. As you use more, it gets cheaper. All abstractions stay the same billing, so a gigabyte in tables is the same as gigabyte in blobs. 1 penny for 100,000 transactions. Something key, a lot of people are asking, how do I get started? I don't want to have this big bill up front. I want to do development. A lot of people already have an MSDN subscription. If you do, you already have Azure credits. So you have, I believe it's 35 gigs of storage, enough compute hours to run a couple instances for the year, SQL credits, everything else. So I would say check that out depending on the level of your subscription. On top of that, there's 90-day free trials available. So if you don't have the MSDN account, just go online. You'll get a free trial. It should be everything you need to proof of concept, kind of kick the tires, see if this works for you. And then lastly, we've seen Azure is part of a lot of people's enterprise agreements. So if you have this, your corporation or your company may already have some credits towards this anyway. And then lastly, on top of that, we ship emulators for storage and compute in the SDK. So now what this lets you do is you can develop your entire application, right, locally before you even hit the cloud. Kind of make sure you get all your ducks in a row and then deploy it to the cloud there before you start incurring any sort of cost or using any of this data. The last thing about this is, in addition to the cost, what you're getting is the durability, the maintenance cost, the hardware refresh. We're right now in the process of deploying what we call the Gen 2 clusters and already in plan for Gen 3. So it keeps getting better and faster over time, and price goes down as we compete. This is really huge because there's a cost associated to having a guy that goes out and swaps the hard drive, right, or repairs the router. All that stuff is done for you now, and you're sharing the same infrastructure as people like SkyDrive, people like XLX Live Music. Some of these really big customers are doing a lot of heavy storage usage. So this is where we are physically in the world. So we have these different regions, and again, these are in pairs. So we have north, south, east, west in America. Again, a pair 400 miles plus away. We have 2 regions over there in Europe, and then the Asia Pacific. On top of that, so this is kind of the coverage, we have CDN POPs is what we call them. So we have 47 of these all over the world. So for those of you that are really interested in media streaming, right, every storage system is going to have certain sort of scalability targets or I/O things that you're supposed to try to stay inside of. What a CDN does is, let's say I need to distribute this 1 gigabyte movie file to 1 million users, right? What I can do is go to the CDN, I can give them the URL of my blob, and say, this is what I want to distribute. And then they'll hand me back an URL, and I can distribute that out to all my customers all over the world. And what will happen is all of these little red triangles will cache a copy of that data locally. So now the performance and the latency for your client is really, really fast because it's been cached in their geography. And they will hit that endpoint, and all this is done for you. All right, so how is it used? Xbox uses blobs, tables, and queues for applications like game saves, Halo multiplayer, music, Connect data. SkyDrive is using blobs to store pictures and documents. Bing is using it. This was really cool. They use blobs, tables, and queues to implement their ingestion engine. So I don't know if anyone uses Bing here, but if you notice when you log in with Facebook or even the public Twitter status, when you do a search, you can see that as part of your results. That feature took one developer 6 weeks to do, and it's all implemented on Azure Storage, and he is able to ingest all of the Facebook and Twitter traffic and get it back into Bing's search results within 15 seconds. You have a quick question. We're going to try to hit them at the end. There's a slide there. I think that's already done. There's a lot of that's in flight, but yeah. All right, and again, we'll try to hit all these towards the end. Again, if you're a small, medium, even a large business, you're getting to use the same infrastructure as Bing, for example, right? Which is a great win. All right, so here's some of the key concepts. We know about storage, we know different abstractions. Let's start to get our hands dirty and start playing around here. So the first thing you'll do, once you have a subscription to Azure, is you'll go and you'll create a storage account. You create a globally unique storage name. account name. And so, for example, blobs would be your account name.blob.windows.core.net. You can, if you don't want to use that URL, you can use DNS to go route to there. You choose a primary location in one of these different regions that we discussed, and then you decide if you want georeplication or not. And then you receive 2 storage account keys. And the key thing here, why 2? Some people think that's a hassle to manage too. The reason is for key rotation. And so what this lets you do, let's say that you have an application, and for whatever reason, somebody checked in or published the key or somehow it leaked. What this lets you do is now you can rotate your application, use that secondary key without ever going down, and then go reissue the first one. Right? So this lets you continuously rotate keys if you need to, so that you never have to take down or redeploy your service. Storage account capacity, each account can store up to 200 terabytes. Obviously, Azure scales way beyond this. What we tell people is if they need more storage, use multiple accounts. And generally, when you're in that case, you're in different geographies anyway. And so you want one on the east and the west and in Asia and Europe, et cetera. All right, so this is very easy to get started. If you go to the portal, literally with an existing subscription, it's 3 clicks. You say storage, create, decide which side of region. You can create a custom affinity group if you like. And then whether you want geo. I actually created a demo account for this. It was spun up. Within a few minutes, I was ready to go and already making requested storage. So it's very, very easy to get up and running. All right, so the first abstraction is blobs. What is a blob? So first of all, there's that URL that we talked about on top. You have your account name.blob.core.windows.net. Then we have a container name and a blob name. You can use the root container, which if you don't want to have that container, is part of the URL as well. So an account has containers. There's no limit on the size or number of containers, as long as you stay within the account limit of 200 terabytes. And a container contains many, many blobs. Again, there's no limit on that. It's up to you what you put where. And then a blob is made up physically of blocks or pages. It's the simplest way to store a large amount of unstructured text, binary data, video, images, with a really, really high level of performance and scalability. Every single blob is what we call a partition. And so the scalability target around that is, we say 60 megabytes per second, basically. If you think you need beyond that, there's different best practices and way to either split out your data into multiple blobs. Storage is so cheap, especially comparing to SQL and some other solutions, that in some cases, let's say I need 120, and it's the same data, I can literally just make a second copy and then distribute out different URLs to each person. If I need to go way beyond that, that's where CDN comes in. It's kind of an ecosystem thing. So now I can distribute this all over the world. All right, so what's a blob container? A blob container can have as many blobs as you want. You can have as many containers in the storage account up to the size limit. A container holds a set of blobs, but on top of that, it has access policies associated with it, if you like. So now what I can do is say, maybe I create a container for a user or for media or something like that. I can create an access policy against that container. If I want, I can make it public to everyone and just directly host website images and things right out of there. Otherwise, what I can do is create policies that I can hand out and with pre-authenticated tokens. We'll get into more of that later. And then I can associate metadata with that container. So for content management systems, things like this can be useful. You can say state or last updated, different things like that. And then I can list all the blobs. And the cool thing about the listing API is we have some functionality there. Since we only allow one level of a physical container, what this lets you do is basically emulate a hierarchical directory structure. So a lot of people have an existing directory structure they're trying to migrate to the cloud, and they say, okay, I want multiple levels all the way down, media, music, et cetera. We can let you emulate that in an easy-to-use way. So what the directory structures can do is basically you use a delimiter in the blob name itself. So for this example, my blob name is media/music/album/song. And now what I can do with the listing APIs is I basically tell it what the delimiter is, and I can list, for example, everything under media/music and not even get anything, just the blob names that are just there. Or I can go anything all the way down to an album, right? It's up to you. So it should look and feel just like a directory on your local computer. The key thing here is that in some cases you have to kind of modify some of the reserved characters into what Azure Storage can hold, and there's a tool to help you do that at the end. In the storage client libraries, again, we wanted to make this really, really simple, so we have this thing called a cloud blob directory to do this for you. All right, so let's do a quick demo. Did a lot of talking. It's easier to see some of this sometimes. All right, so first thing I have here, at the very top, is my account string. This is just saying, and And my account key is here. Best practice is to not project this in front of lots of people. But since this is a temporary account that I'm going to delete later, it doesn't really matter. So I have an account name, and right here I'm going to say I'm going to use HTTP. Again, especially if you're sharing your blobs, HTTPS is a good idea, but we want to be able to see our traffic. So I have a tool here called Fiddler, which is really useful when you're debugging applications that hit the web. So the first thing I'm going to do is just create a storage account. Now, a storage account basically is everything you need to hold all the information about your given account. The model that we have in our client libraries is to give you a local reference to an object that represents something on the cloud. So now you have this local thing, and it feels like a local file. It feels like a local directory. But by doing methods on that object, you can do something in the cloud. On top of that, all those operations are consistent in the fact that they all have, for example, a retry policy. You can disable it if you like, but that can handle fault-tolerant scenarios, right? So my internet connection drops or something goes low or whatever. Now I can back off and retry, things like that. Okay, so this line I have here, we have an easy-to-use helper if you want to point towards development storage. So I actually have this little SDK installed. That's all I have to do to get storage emulator up and running. You should see a little pop-up there. It says I'm running. If I wanted to, again, I could point towards that. It's basically a local database on your computer, and I can develop against it. So for this purpose, we're going to develop against the cloud. So here's our very simple hello blob. Okay, so we have our account, and now we want to do something with blobs. So we're going to create a blob client. And then we want to get a reference to a container called SPC demo. Okay. Now again, nothing has happened. We haven't gone to the cloud. If you look at Fiddler here, you haven't seen any traffic. We're doing this totally on the client side. So now we're going to do something called create if not exist. Or you can do just create, or you can delete, etc. So this goes out and makes sure that that container now exists. So there we go. And now I want to upload just some very simple blob data. So we'll just say, hello SBC blob. Okay, so we had a reference to a container. Now we're going to get a reference to a blob. And we're going to upload that data. So in this case, I have a little bit of code there to get the encoding in a memory stream and send it up there. If you have a file stream, this is really easy. You say file open. You basically give it the stream, and this is all handles everything for you. On top of that, a block blob, and we'll get to that later a little bit more in depth, but you can do a single blob put up to 64 MB, right? So it's a single atomic transaction. Anything over that, you need to upload individual blocks, and then we'll do something called a put block list, which basically defines what the blob is. So this is, again, best practice, and everything is in the box for you. So it's going to decide based on the length, you know what, I can do this as a single put. So if you look at Fiddler here, you can see there's my data. Now I want to download that, download the stream. All right. And then we should see, there we go, we retrieved our data. Hooray. All right. So we'll switch back over here. Again, very, very easy to use. We have people doing very high-scale applications using this client. The latest 2.0 release of the client library, we've seen dramatic performance improvements, and we're actually targeting some of the fundamentals even more. And so this, we're really, really driving down latency, CPU usage, things like that, which is helping people use less infrastructure, which is great. So what can you do with a blob? You can create it, you can delete it, you can set these permissions. We call them ACLs or ACL policies. There's metadata. You can do parallel uploads. Single range gets, this is useful, for example, for media streaming. Let's say I did upload a single blob. You could do a get and say, give me 0 to 1 megabyte. Now give me 1 to 4 megabytes. Now 4 to whatever. And you can kind of seek around a blob as you'd like. In addition to that, in the client libraries, we have a stream implementation that'll do local buffering for you. So you can say, I need to consume this data. I don't want to download all 10 gigs right now, but I need 1 megabyte at a time. So you say the read-ahead size is 1 meg, and then you just get a stream reference, and just like a file, you start reading it and consuming it. And as you get to the boundary, it'll prefetch that next chunk of data, and then you read out of the buffer. We have snapshots. This is really cool for versioning because you don't pay for a second copy of the data. So let's say I have a blob that is 10 megabytes of A's, and then I snapshot it, and then I upload 10 megabytes of B's. I'm not paying for 30 megabytes in that case. I'm paying for 20 because that first 10 is the same between the snapshot and the actual copy. And then later what I can do is promote a snapshot or some sort of back up to the current edition of the blob. So for backup and different versioning things, this is useful. We have something called leases, and now you can use this for locking, for master election. So you can take a lease on a blob and just say, basically, no one can touch this blob unless they have this lease that I have. And then you can renew that lease and break it. This is really useful in a distributed system. All right, so the types of blobs. We have the block blob. Everything is uploaded a sequence of blocks. The size limit is 200,000 megabytes. Some people like to say that in terms of gigabytes, I think it's actually 196 or something like that if you do the math. The reason being is currently you're allowed 50,000 blocks. Those blocks can be up to 4 megabytes each. Each block is identified by a block ID. For example, if you wanted to use some sort of circular buffer, if you wanted to, a put block list, you could take the block from the beginning and put it on the end. And that could just be an operation. You didn't actually have to do any data downloading and re-uploading in that case. A page blob, target at random write workloads. Each blob consists of an array of pages. The cool thing here is you pre-create the size, and you can grow it later, but you don't actually pay for that data unless you write to it. So let's say I create a terabyte page blob, and I write 1 megabyte. You're charged for 1 megabyte, not the 1 terabyte. If you read it, you'll still get the zeros as if it is 1 terabyte long, but since that storage doesn't physically exist yet, you're not billed for it. Again, the writes need to be 512 bytes aligned. All right, so here's how you use a block blob. One of the best examples here is to upload the movie The Blob. So it's a 10 gigabyte movie. So the first thing we do, we decide our blob name. So we're having The Blob. And then, again, if you use the storage client library, this is done for you. If you want to do it yourself via REST or whatever, you can do that as well. So what happens for you is a bunch of block IDs are created as you upload. So you put blocks. There's put block 1, put block 2, put block 3, and so on, all the way to block n. Okay, so now the server has all of these blocks. If you were to go and try to download this blob, it doesn't physically exist yet. They're actually stored in what's called a temporary block list. So now I follow this up with a put block list. And this is the thing that'll take all of these blocks, chain them together, and say this is what a blob now is. And now you can start immediately accessing it after that. So you see all the different block names there. That's actually in XML. But again, for client developers, most people won't even ever see this. It's just how it actually works. The cool thing about this is those blocks don't have to be uploaded in any given order, right? If you wanted to, you could upload them backwards. But what this really helps us do is do parallel uploading, especially when you have these large virtual machines in the cloud, right, with 8 cores and a big fat pipe. It's nice to have 8 simultaneous connections or whatever logical processor number you may have. So it's efficient. The other cool thing here is on continuation and retry. So let's say, with a naive case, I wanted to upload 10 gigabytes, and some sort of I/O exception happened. You don't want to start back at byte 0, right? So now by uploading this in chunks, each one of these operations is surrounded by a retry policy and made fault tolerant. So one of these guys can fail, and only a small amount of data will have to be retried. And again, if everything works right, it should be totally seamless to the user. Parallel and out-of-order upload of the blocks is possible here too. Each block can be up to 4 MB. Each block can be a variable size. So you don't, if you're doing some sort of buffering thing, right, especially with media that may not have a fixed block size, you could have a 1 byte block, you can have a 4 MB block. It doesn't really matter. The only key consideration there is you can only get 50,000 per blob. And each block has a block ID associated with it. The key thing there is those are scoped to the blob name, so you can reuse them across different blobs. The different operations, you have put block, and then you have put block list and get block list. So you can actually download the block list of what this blob is made up of, and then reorder it. Or if you want to do some sort of truncation, you could literally just do a put block list minus the first 3 blocks, for example. All right, page blob, random write. So the first thing we do is we'd create a blob. So in this case, we're going to say it's 10 gigabytes. All right, so now this is allocated in storage. This has a fixed page size of 512 bytes. Now we're going to do a bunch of random I/O. So the first thing I did is I wrote pages 512 to 2048. Now I'm going to do a put page for the first kilobyte, and I'm going to do a clear pages, right? And so I didn't actually have to upload any data, but I just said wipe out this data here, zero it out. So I cleared the pages between 512 and 1536, and then I put one more page. Now when I do get page range, I can see that the server is having 0 to 512 and 1536 to 2560. And basically what happens is now I can ask the server out of this 10 gigabytes, what ranges have data? Again, if I do a range get, I'll still get the zeros. So for example, if I do a get blob from 1,000 to 2048, 1,000 not being 512 byte aligned, I will still have zeros for the first 536 bytes. And then the rest of it is the data I stored there. So again, random read, write operations, this is great. Some of the details, page blob is created with a maximum blob size. You can change that at any time. And the address space we talked about is broken up to 512 bytes, pages. The different operations, you can do a put page. That's limited to 4 MB. And then you can do a clear page. So now you can just say any sort of range, just wipe out this data without having to re-upload zeros. And then reading it, get blob, same exact API as a block blob based on range. And then a get page ranges. So now you can see what data is stored in the blob. You're only charged for the pages that are stored there. Again, not the zeros. All right, Azure disks and drives. So we provide this durable file system for you, this page blob. What are some of the compelling reasons to use it? We have something called disks and drives. So for infrastructure as a service and platform as a service, these kind of play in different ways. For infrastructure as a service, for the disks, you have the OS and multiple data disks associated with a VM. These are network-mounted durable drives. So now you get to talk to it just like a hard drive. And that data, any unflushed data and unbuffered writes, are made durable to the storage system. Platform as a service, you can dynamically mount network-attached single-volume VHDs. They're fixed formatted VHDs. Everything's stored as page blobs. You can just download this as part of the SDK. Basically spin up hard drives and write to them like files. All right, so now we decided, OK, blobs are great for my use case. How do I decide what to use? Again, block blobs, streaming workloads, and depending on the update semantics you may need, you can update those, use those smaller blobs for a single operation up to 64 MB, or upload a bunch of blocks. And then page blob, again, target at random read-write workloads. The update semantics there is immediately when I write, it's available everywhere. So for example, in the block blob case, let's say I was doing some sort of live streaming scenario, right? And I need to append 512K at the end of the blob. That is not visible to someone unless I do a put block list. So there's actually a two-phase commit in that sequence there. And that's not a single atomic transaction, right? So I may consider this, for example, for page blob or something, where I do a single write, and that data is immediately visible. All right, so tables. And again, we're not going to spend as much time here. Tables is our NoSQL table database in the cloud, basically. And this, because it's NoSQL, because you don't have things like joins, it's non-relational, we can scale to what we call web scale, right? We're not talking about gigabytes anymore. We're talking about terabytes and petabytes of multiple accounts, things like that. So just like blob and Q, we have the base URL here, account.table.core.windows.net. So you have different tables. Again, there's no limit on the number of tables. You can think of it as the analog to the cloud blob container. So this is where I can set those permission policies and the like. I can create a table. I can delete a table. The nice thing here is, let's say I've staged a gigabyte of data. I don't have to download and delete all this data individually. I can just wipe out the table in a single operation. And then tables has entities. And the key thing here is, since we are NoSQL, we're schemaless. So a single table can store all sorts of different types of data right next to each other, side by side. We have a single clustered index lookup there. And so now what you can do, for example, when you have customers and orders, you don't have to have a customer orders and a customer table and an order table and some sort of relation between the two. You can stick that in the same exact table. And if that data has the same partition key, for example, a user ID or something, I can do a single atomic update. So if you think about the example where I have a customer account and he has some sort of balance with me, right? He also has a bunch of orders, and I want to place an order. So I want to add an order to the table, but I want to debit his account by $100 or whatever it is, right? If those are in two different places, this may be a hard thing to do because I have to go and debit, and then I have to go and place the order, or vice versa. And then if one of those things succeeds and the other one fails, I have to do some sort of rollback logic. And then on top of that, if the really unlucky case where I can no longer access one of these for whatever reason, now I have this kind of bad state where I've either debited him but not placed the order, or placed the order and not debited him. That's not a great thing. So by allowing you single atomic group transactions, you can do this thing where you're editing the first entity, saying, OK, take $100 off, and insert this order. And that atomic transaction will happen either altogether be a success or altogether a failure. So you don't have to worry about all this rollback and transactional stuff. So again, designed to scale to terabytes and beyond. There's a large demand for economically accessing structured data at internet scale. With a relation database, what you'd have to do is as your database size gets larger, as you have millions and millions of records, you start having to scale up not only the database size, but the hardware backing it. On top of that, at some point, you start hitting these limits where you have to shard out your database anyway, right? And so you start losing some of these nice things about a relational database, like doing joins and things across these different things, databases. So you end up doing manually sharding. You have to have some DBA experience to kind of administrate this thing. So here's the basics of Windows Azure Table. Flexible schema, again, there's no fixed schema. There's 3 reserved properties in every entity, partition key, row key, and the timestamp. And then the rest are up to you. And so, again, side by side, having different data. We have a single index, which is your account name, the table name, partition key, and row key. So that is optimized for lookups and for queries. And then, again, you can query over any other properties. There's just not another index for those. The row key is what gives you the uniqueness within a given partition. And then any data that has the same partition key can, again, use this atomic entity group transaction semantic. So it's optimistic concurrency. What this lets you do is, since every entity is stateful, it has a timestamp, everyone can download the entity, and then we can both try to update it, and one will be a success, and one will be a failure, and then you'll have to re-download, et cetera. So it's optimistic concurrency in that way, but you, again, don't have to worry about all this rollback stuff and trying to figure this out on your own in your application. For the query, that you can do a single entity lookup, what we call a point query. So you basically say, I need this partition key, this row key, and that's really, really fast. You can do a scan, where you say everything above this partition key, or below, et cetera. And then the performance of that query depends on the selectivity of your query. On top of that, we have something called server-side projection. So these entities can actually be quite large. We'll get to some of the limitations. But an entity itself can be up to a megabyte and have 255 properties. If I just need to, for example, download my employee table and give everyone a 10% raise, what I can do then is just do a select and have the server only send back to me the salary property instead of the address and all the other properties an entity may have. And I can update the entity back to the server without having to round trip all this extra data. This is exposed, again, via REST APIs, and specifically for tables, we use something called the OData protocol. It's an open protocol. You can go to odata.net and look at it. Again, in the client libraries, we handle all this for you. All right, so every entity has these 3 properties. Each entity can have up to 255 of them, and each property can be 64 kilobytes. A single entity can be 1 megabyte, and a batch transaction can be up to 100 table entities or 400 megabytes. All right, so we'll do a quick demo here. All right, so we did hello blob. Let's do hello table. So this should start to look a little similar to what we had for blobs. So we're going to create a table client because we want to operate with in tables. And then we're going to get a reference to the SBC demo table. We're going to create that. And now we're going to do, in this case, we're going to work with something we call POCO objects, plain old CLR objects. We have something analogous in Java and things like that. All you have to do is if I look at this entity, is I've derived it from the base entity that comes in the SDK, which has partition key, row key, timestamp, things like that. And I've exposed one more field called text. So all I have to do to persist something here is expose a property type that's gettable, settable, public, and is one of the supported types, like int, double, string, GWID, byte array, things like that. So I'm just going to create a bunch of these entities. So in this case, we'll just do one. So we'll upload some data here, and we'll say, hello, table. All right, so a single line is all I need to insert that entity into the cloud. So you can see, again, this all this XML is done for you. This is that OData protocol that we had talked about. And now I'm going to do that point query where I'm going to retrieve that entity in a single line. So if I go back here, you can see that we successfully round trip that. Now we're going to do that atomic batch update. So let's say, for whatever reason, I didn't want that first entity, but I need these other ones. So what I can do is define a batch. I can say delete that first entity. And now I want to insert 5 new ones. So again, in a single line, I will execute that batch. And now what I can do is query that back. So I create a table query. I'm going to just iterate over those, count how many I have, and write out that text. Look there. Okay, so we retrieve 5 entities, batch 1 through 4. You'll notice that the first entity is now deleted because that was done as part of that single atomic update. All right. All right, so queues. Queues are, again, going to help you with decoupling components in a distributed application. So if you think about the scenario, I talked to someone yesterday or 2 days ago where they said, we're uploading thousands of documents in TIFF format, and I need them to do OCR and generate PDFs and do all this work on each one of these documents. So now what I could do with queues is I could have some sort of tool. We have actually a tool for mass blob uploads that we'll get to later. But I could upload all that data, and what I could do is insert messages into the queue saying this thing needs to be processed, right? And what that lets me do is, again, my application knows nothing about who's doing the processing or how or has any sort of endpoint information, so it's decoupled. There's no sort of timing issues of waiting for this guy to do any work. I'm just saying, here's a message, I need this to be processed. And there's some semantics there that make sure that no matter what, this message will be delivered. So again, similar to tables and blobs, we have a container, which is a queue, and then we have messages inside those. Those can just be any sort of data, text, byte array, whatever, up to 64 KB. So the operations, create, delete, set, ACL, again, that's similar to the other abstractions. You can queue a message up to 64 KB. The quick note here is because of the mechanism we use for guaranteed message delivery, although it's called a queue, it's not guaranteed FIFO. Some people think that, oh, it's a queue, it must be first in, first out. That ordering isn't guaranteed. We have a lease mechanism. You can get a single message or get messages, depending on how you design your scenario. And then you can delete a message. The delete, it's a two-phase delete. So the first thing you'll do is do a get message, and then later, after you do some work, you'll go back and delete it. When you do the get message, it becomes invisible in the queue for some amount of time. So now other roles won't get the same message and do the same work. However, let's say after 3 minutes or whatever else, your role falls down or fails or whatever else, and you don't go back to delete the message. That message now becomes visible in the queue again for another worker to process. So in the case of a failure here, we've guaranteed this message gets delivered. On top of that, the metadata on the message, we have message count, which you can use for scaling, and then also a DQ count per message. So now what I can do as a role, I can get a message off the queue, and I can say, how many times have you gotten retrieved? Let's say I have some sort of threshold, and I say, wow, I've tried to process this message 5 times, right? And this message maybe be pointing me to these 3 blobs or something. And for whatever reason, after 5 times, I haven't been successful. So maybe there's something wrong with this message or this unit of work or this blob that's causing me to fail. So I can call this my poison message scenario, and what I can do is take that message, stick it somewhere else so maybe someone can investigate it, and take it off the queue and keep my application running, right? If I just kept trying to naively DQ and process, and let's say in the worst case, this was throwing an unhandled exception, my role was dying, right? You would just spend forever spinning up and down roles. So this helps you detect those scenarios and work around them. And again, we have sharing scenarios, all 3 of these. We'll get to it in a second here with shared access signature. So here's a quick demo of queues. So we have a queue. We insert a whole bunch of messages from different roles, or because of SAS, you can use, this literally could come off your phone or your device or anything. So the time is 7 o'clock, and the first worker role gets a message, and it's going to expire in 5 minutes. That's its invisible time. Okay, so now we move to 7:04. The worker role says, I'm not quite done any more time, so it extends that time out another 5 minutes. Periodically, as I do some work, so let's say I have a 3-stage process, I need to do OCR first, and then maybe I need to render a file or different things. I can update the message with some data up to 64 KB, or maybe I just have it saying, okay, this was 10 blobs and I've done the first 4 or something like that. Again, this is still invisible to the rest of the workers. Now, we move on, 7:07, something terrible happens, my server sets on fire, something bad happens, and this role falls over. Okay, so 7:09 comes around, and this message, with its updated state, now becomes visible again in the queue. So worker role 2 is able to download this and resume from basically the same point as the first worker role without duplicating that effort. And again, we haven't lost any sort of transaction here, right? We're going to make sure at the end of the day, all of our documents have been processed. All right, so we'll do a quick demo here. All right, so again, same thing. We'll create a queue client and a queue. The difference here, what we're going to do is we're going to add 2 messages to our queue, and we're going to give them different invisibility times. So you can make a message initially visible, or you can give it an initial timeout, or invisibility time. So I have one at 20 seconds, one at 30 seconds. And then what I'm going to do is I'm just going to go into a loop and pull for messages to see when work shows up. So we'll just run this. Okay, so I have this updating, and it's going to the queue every 2 seconds right now. Again, with the transaction cost, and especially if you're in the same data center, that bandwidth is free. The transaction cost is very, very low now, a penny for 100,000 transactions. So even in the polling case, this is still economical. Okay, so I've polled. We're getting to 20 seconds. Okay, there's that first message. We've retrieved it. We deleted it. We keep polling. Still, there's nothing there. When we get up to 30 seconds, we see the second message come down. And there it is. So now my queue is empty. On top of that, let's say that you have some sort of recovery logic. You could easily go and just say, clear out the entire queue. I want to start over, whatever. I don't have to go through and wait for all these messages. All right, so let's talk about scale. We've actually been doing a huge rollout of this Gen 2 cluster, and we've changed the network topology as well as the hardware. We used to have kind of a tiered hierarchical network, and we've gone to this fully meshed, what we call flat network. We've also moved to a software load balancer. So it's this quantum 10 network. We have non-blocking 10 gigabit to all the nodes. It used to be 1 gigabit. On top of that, with the software load balancer, this is really helping our scale. And the aggregate backplane is in excess of 50 terabits per data center. What this is letting us do is these scenarios like infrastructure as a service, high IOPS scenarios are really, really coming into play here with this new hardware. So there's a blog post at the bottom there if you want to read more about this and the different changes have been made, but also what this has let us do from the storage side is up all the scalability targets for new storage accounts. So on an older storage account, for example, a table partition would say you can do 500 entities a second. On a newer one, past June 7th, I believe it's in the blog post, you can do 2,000. A capacity is up to 200 terabytes. Transactions for the entire account is up to 20,000. Again, this is at the account level, so if you need to go over this, all you have to do is create multiple accounts. The bandwidth for geo-redundant, so I have that geo backup enabled, is 5 gigabits in, 10 gigabits out. And if I use locally redundant storage, and again, we recommend this when you can easily reproduce the data. So some of the high-performance computing stuff where you have some sort of base set of data, but I can generate this again. That might be something to use locally redundant data. The bandwidth is actually up to 10 gigabits in and 15 out. All right, so the scalability targets for a partition, this is by the end of 2012. This applies again to those accounts created after June 7th. In the portal, if you sign up, if you get a new one, it's already past that. But if you have an older existing one, you can see in the portal in the lower right-hand corner when it was created, if you have any question. A single queue is up to 2,000 messages a second, table up to 2,000, and a blob, same account container blob name up to 60 megabits. And this is just kind of where we are as of June in terms of scale. 4 trillion objects, average of 270,000 requests a second, 880,000 at peak. There's been a 4 times increase over the last 12 months. And again, this is June, so I'm sure these numbers are already way outdated. All right, so let's talk about the scenario, again, for the SharePoint developer. I want to host these huge document collections and these media files, right? So now I understand what storage is. How can I use it? So what we want to do, if possible, is share this data out. And what would be great is if I didn't have to have this huge farm of servers to just be able to serve data that exists over here in storage. Instead, it would be great if I could do, in a secure way, allow users to go straight to storage, right? Because now I don't have this extra network hop. I don't have to have as big of a service up here, right? So we have some scenarios around this. The first thing is full public read access. So on a container, you can physically say, everyone can read this thing. And literally, it will look just like, if you want to put the URL on your website of an image or whatever, this is where that would come into play. A client could list all the blobs in a container via an anonymous request. They don't have to have any sort of keys or authentication. The only thing they can't do there is enumerate the containers inside your storage account. Then we have public read access for the blobs only. So now, again, you can get to the blobs, but the container data is not visible. And you can't enumerate the blobs within a container. And then no public read access, this is by default. So now the only way to get to this data is if you have the storage account and key. All right, so then we have this thing kind of in between there. So we have private and full public, but now I have Active Directory and my SharePoint user, and I know what someone's allowed to read. So it would be great if I had some sort of intermediate thing where I can say, it's not public, it's not private, but just you can read it. And especially, it would be great if I could say, you can read it for an hour. And even better, you can read it for an hour, but if I see that you're going too slow or you're not, maybe you've reposted this link all over the internet and you're reading it too much, I'm going to revoke that. And that's where shared access signature comes into play. Again, being on top of the same data store, we have shared access signature for every single abstraction. So for table, for instance, I can give you permission to a single row in a table and say, for your user gamer score or whatever, you're allowed to increment that yourself, right? But you're not allowed to delete it, and you're not allowed to add other records. For blobs, again, the permissions are up to you. So SAS allows you to provide granular access to a third party without exposing that private key. And again, the private key is the keys of the castle. We don't want that to be leaked out or given to other users. You can tie this optionally to a container, so a blob container, a table, or a queue. So now what this lets me do is I put the permissions on the container, and then I have the signature reference that policy. So now let's say something terrible happens. I gave this URL to a trusted user, and then he posted it on the front page of Reddit or some website, and the whole world is downloading it, and I didn't want that to happen. What I can do, the first thing I could do is go to the portal and just reissue the storage keys, and everything would fail. That's not great, because now I've impacted all the rest of my users. So now the second thing I can do is I can just go to that container and wipe out the policy. And anything that references that policy just fails, and then I've solved my problem right there. So that's really good. I have granular access at the container level up to 5 policies apiece. If I want to, I can just issue it at the blob level, for example, that is not tied to a policy, and I can just do as many of those as I want. The only trouble there, if I don't, let's say I have the expiry for max time or whatever, again, if that token leaks, it's up to me to rotate my storage keys on the entire service. So again, this is a pre-authenticated URI for a given resource. So we'll do a quick example here. This is the anatomy of a SAS token. So all of this travels as the query string in the URI of a resource, right? So the first thing I have is the version of SAS. The second thing, I have the start time. And then I have the end time. So this token's only going to be good between this time range. And the important thing to note when you're using SAS is clock skew, right? Your client device may not have the exact same time as my server. So sometimes when I'm issuing these, for example, I will add, or I'll subtract 5 minutes from the start time and add 5 minutes to the end time or something like that to account for clock skew. Again, it's up to your scenario. If you have some great thing to synchronize clocks, then you know what those margins should be. The next thing for blobs is I'm accessing a blob. And then the permissions, I'm going to give them read-only permissions, so SP equals R. And then this signature is based on my storage key, but I've still kept that private. Now, everything on the bottom part of the screen there, all I have to do is append that to the same URI of the blob, and I can just hand this out to anybody, and they can download that blob. They can't upload because I didn't give them right permissions. You can use the storage client, so if it is a client application that uses our SDK, they can take advantage of, for example, the stream abstraction that we provide, or parallel uploads in the case of write, any of that. Or, literally, you could just stick it right in a browser. There's some best practice around that we'll get to in a second. So now we can do a SAS token based on a policy. So in that last one, I didn't have revocability. The only way for me to invalidate that signature was to wait until the expiry or rotate all my storage keys. So now what I've done is I've uploaded a policy to the server, let's say on the container. So I have the version, I have blob, but I don't have a start time, I don't have an end time, and I don't have the permissions. Instead, I just have assigned identifier, which is a policy name. So I've uploaded a policy called read policy. This signature reference is read policy, and now I've signed this whole thing. Again, I put this whole thing in the query string to the URI to the user. Now, what I can do on the back end is just keep updating this policy. Maybe life is good, I keep extending it by an hour or a day or whatever. Or, for whatever reason, I want to revoke it, I can do that as well. So here's some of the best practices around shared access signature. First of all, when you're issuing these tokens, use HTTPS. The reason being is it's a pre-authenticated token that's part of the resource itself. So let's say you're at Starbucks on your laptop, on an unsecured Wi-Fi connection, someone sniffs the traffic and sees your token go across the wire. They can replay that request in any browser or whatever and download your data. right? So if you use HTTPS, you've tunneled through that, that's kept secure. Use the minimum permissions necessary, right? Don't give them write, read, delete access when they only need to read. And again, for the time period, they probably don't need it for 100 years. They might need it just for a day or an hour. Again, when you have a service stood up in the middle, what you can do there, and what we call the SaaS provider model, is now I can have my client talk to the service, get the token, and then let's say for whatever reason he's on a slow machine and needs more time, he can just go back and get a new token and keep downloading. Clock skew, you have to account for that. And again, whenever possible, make these SaaS tokens revocable by tying them to a policy on a given container table or queue. The other last thing there, some people think, okay, I revoke this read policy, but I still need a read policy. And so they'll put another policy in there called read policy. Since it has the same name, that token that you were trying to revoke is still valid for the new set of permissions. So if you are doing this revoke scenario, make sure you've named that policy something different. All right, so this is the SaaS provider model. We're going to start to put all the pieces of our scenario together. So the first thing I have is my public service. This issues a SaaS token. As a SharePoint developer, you can think of a document collection, for example. You could update all these links when a user comes here, and now they can just take these links and download them. I issue the SaaS token to the device, or the role, or whoever's reading the storage, or writing the storage in this case. And then the device goes and accesses storage on my behalf. On top of that, something we'll get to is we have something called analytics and logs. Logs and metrics, which collectively we call analytics. What this lets me do is now someone is talking to my storage account without me knowing, but now I can audit logs and access and see, okay, maybe this user is doing too much upload. Maybe he's my most active user and I want to reward him or something, right? So I can go through those in a time-based way and see who's accessing storage how. On top of that, this gives you a lot of monitoring and self-diagnosing for your application. The cool thing here is now my public service only scales as much as it needs to issue these links, right? So let's say in the media example, I'm serving a whole bunch of these 10 gigabyte blobs. In that case, in the traditional case of like a 3-tier application or even SharePoint, right, my service would have to get just larger and larger to handle all of this throughput because it's reading and writing back out to the client. In this case, the service only has to get as big to have the capacity to issue these tokens, right? So it can be, in some cases, order of magnitude smaller, and then all of that high I/O throughput goes straight to storage, right? On top of that, the back end of Azure storage, we've talked about before, is scalable by definition, and we auto-scale. So the way you tell us to scale is by reading your data, and then we split that out and serve it by more and more servers on the back end. So we will scale out to meet the demand of how you're accessing your data. Devices and role will now access storage directly using SaaS as the preferred model. Again, you can do public for websites and static content. There's no routing overhead. You've saved yourself an entire network hop. And then we use analytics to monitor the storage usage. Client applications can make use of the storage client library if they want. Again, to use that best practice. For example, download resume is a great one. There's some scenarios there that we protected against that a lot of times aren't obvious to the user. For example, let's say I have a blob that has all A's. I start downloading, I get the first 5 gigs and my network drops off. Well, in the meantime, if someone has uploaded all B's, if I just started resuming and downloading the last 5 gigs, I would have invalid data. The first half would be A's, the last half would be B's. That data never existed in the blob. So what we've done is with the concurrency model, our download resume will check to make sure it's the same state, the same version of the blob. And if the blob no longer exists, we'll just throw and say, hey, you need to start over because this blob doesn't exist. Or if it is the same version, we'll just continue and you won't even know something happened. All right, so let's do a quick demo here about how to share the blobs. All right, so this is going to look hopefully more and more familiar here. So the first thing, I have a cloud blob client. Get the same container reference, and we're going to use that same blob, so I don't need to upload it because I already have it there. The first way here, I'm going to create that read policy. I'm going to generate a signature straight to the blob, but I'm not going to tie it to a policy, just to show you how to do this. So I'm giving them permissions read. I'm going to start it now minus 5 minutes, and I'm going to add a day. So this will be valid for 24 hours plus 5 minutes. So all I need to do to generate this token is take the URI of my resource and add the signature. Right? So if I look at this, I have a pre-authenticated token. I can just go to my browser here, Paste that in, and there's my blob. Again, I didn't use best practice here in the sense that I use HTTP. All I'd have to do is update the front of this to use HTTPS. And then if we load Fiddler here, we'll see these tunnel connections here, right? So now that person sitting at Starbucks can't get your data's safe, life is good. All right? And now the second way, so that was the easy way to do it. Now we want to make sure that we tie it to a container. So now what we're going to do is we're going to create a set of blob container permissions. And then this can have, again, up to 5 policies. So we're going to add that policy. We're going to call it read policy. And then we're going to do this operation called set permissions. We're going to store that on the blob container. And now we're going to generate a new signature. And instead of passing in the policy like we did before, we're just going to pass in null. And we're going to say, reference the read policy. All right, so if you look at this, URL is significantly shorter. But again, I can go download my blob. If I were to go and wipe out that that policy on the container, this would fail now, right? So the revocability story is there. All right. Cool. All right, so now we're going to get into analytics. So far, we've gotten our service to the point where my service is smaller, my SQL database is breathing much easier because I have all this data outside of it. My cost is down because I'm having users access storage at literally pennies for the month per gigabyte. Now I want to figure out, okay, this is great, but I want to audit and see what's been happening on my account. So we're going to look at analytics. We have 2 different things here. One's called metrics, one's called logging. Logging is a per-line log. Every time something is accessed, you get a log entry and a whole bunch of information about, for example, which client accessed it, what the URI, if they use SaaS, things like that. Metrics is about usage, right? What was my ingress for this hour? What was my egress? How many times are these blobs being downloaded? Things like that. Logs and metrics are stored in your storage account. The nice thing here is there's something called a retention policy that you can associate this. You can configure this per abstraction. So for example, if I only want logs and metrics for blobs, I only have to turn it on for blobs, not tables and queues. And there's different kind of levels of that. But then what I can do is I can say I only need to retain 4 days of logs. After that, it's already happened, life is fine. Now what the server will do on your behalf is go and delete all the old logs. And you don't get charged any transaction costs or anything. So you don't have to worry about GCing these things and these just growing forever. So the only cost to you to turn this on is literally the storage that the logs take up for a month. And again, depending on your retention policy and the activity, this can be either quite small or quite large. It's up to you. There's a way to enable this via code, via the storage clients, or it's actually been put in a nice UI on the portal. So literally all you have to do is sign into your portal, click a few boxes, and you're up and running. This is especially useful to use when you're using a SaaS scenario because you're not controlling the client's behavior necessarily, when they download something, how often they download. So logs are recording the requests. They're stored in blobs. They're text files with 1 line entry, or 1 entry per line. Each blob can contain 1 to many requests. They kind of break out based on time and also a certain max log file size. And a request typically shows up in the log within 15 minutes. You can configure the logging levels separately, and we'll show you that on the UI in a second. One key thing to note, this is best effort logging. So the logging is done by what we call our front ends in our service. If some catastrophic thing happened immediately following a request and it wasn't able to flush out the logs, it's possible that 1 or 2 of these lines wouldn't make it. So if you're using this for like financial transactions, for example, you have to be aware of that and maybe put your own sort of logging mechanism on top of that. For most general purpose things, for auditing, for debugging, everything else, this works really well. So here's some of the just various data fields that we log: the account, the service type, the request role. We have something called the client request ID here, which is nice because especially if you if you control the client application, let's say I make a Windows Phone app or a Windows 8 app, I can specify a client trace ID with every single request that hits the server. So now I can even go down and figure out this was Joe, or this was this user, or I could, whatever string I want to put in there, I could say, and he's accessing it on a Windows 8 device, and he is doing it from this geography. It's totally up to you, whatever you want to do for not even just the entry of the log, but the trace ID of how this access was made. And this is how easy it is to enable logging via the portal. There's a page here. You go here, you see blobs, tables, queues, read, write, delete, and a retention policy. So you go in there, tick a few boxes, whatever you need logging, and it'll be enabled. Again, the retention policy in 0, that means that we're not going to delete them for you. In any other integer, you can say 7 days, 2 days, whatever. It's at the day increment. All right, so why turn on metrics? So we did logging, now we're going to talk about metrics. Metrics is really useful for diagnosing my application, especially when I get to scale things. Again, for example, in the media delivery scenario, where I had this great scenario where I uploaded a blob and now I gave out that URL. And that worked great up to the scalability target of 60 megabytes per blob. But then this got really, really popular and everyone started watching it at the same time. So now maybe I'm seeing my latencies go up. And I want to figure out why is this happening. Well, now what I can do is I can go to metrics and I can look in aggregate over time what's happening to my storage account. So this is really easy for self-diagnosis. And then I can take appropriate actions. If it's exponentially larger than what I expected, then I need to start using something like CDN or some sort of local caching. If maybe I'm just needing, let's say, 120 megabytes per second, I can do something like maybe make a second copy of the data in blobs. Use something like IS smooth streaming where the blobs are literally chunked up, right? So now each chunk is in and of itself a blob that has its own 60 megabytes per second. And again, once you have a finer grained partition scheme, which in tables is a partition key, in blob it's the physical blob, in queue it is a single queue, the service can now scale that out more and more based on the read or write pattern. So transaction metrics are provided every hour. You can see a few of the different metrics we have here: total transactions, availability, ingress, egress. Capacity metrics are for blob right now. And then, again, on the portal, you go there, there's a few boxes. You can say minimal, verbose, and the retention policy per abstraction. The key thing here is that they're stored in different places. So you can see here that all the logs are stored in $logs. And all the metrics are in the table called $metrics. So again, if you want to, you can use a storage client or some sort of third-party browser. There's actually tooling even integrated in VS to browse these, download them, delete them. Or you can do it programmatically, aggregate these together. $logs and $metrics, one key note is this: they have separate resource limits, and so they don't affect account level throttling. So this isn't going to become the bottleneck of your application. The cost, again, it's only the size of the data. And then any sort of transactions for when you're accessing that data. So if you're reading it, any bandwidth egress, things like that. All right, so now back to our scenario where we have lots and lots of documents. We want to push them up to the cloud. How do I do that? Wouldn't it be great if there was just some easy command line or PowerShell thing or something like that? So we have this tool that we've just released. There's a link there. You can download it. It's going to be a blog post, and I'll point you to that in a second, with some more usage and things. But basically what this is Xcopy for the cloud. So I have an existing application. I've got these 10,000 documents. I'd love to shove them up in blobs. And then I want to, again, maybe use queues to trigger off the processing, the go and update my SharePoint databases with all the good searchable indexes, things like that. Azcopy, literally you can say, here's my directory, I want to be recursive, here's where I want to send it, here's my key. It'll do all that for you. It'll do parallelism and fault tolerance and things right there out of the box. You can specify wildcards for certain types of files and things like that. So here's an example. I have my c:/blob data. These are all the docs that I want to shove up in the cloud. And I want to go recursively. So if you see at the bottom there, I have subfolder 1. Now again, there's certain characters in the cloud that don't make sense, and I would love to maintain this hierarchy of data, right? These different directories, so that I can list them in intelligent ways later. So what Azcopy will do is, based on a predetermined set of rules, is change any sort of reserved characters for me. So the first thing it does, we're uploading a bunch of these documents. Again, this can be done in parallel. This is great. I get down to subfolder, and if you see what it did there, it moved that to a /. So again, using the Cloud Blob directly in the storage client or the listing API via REST, I can now list everything under subfolder 1, even though physically it's sitting right next to car1 in terms of the blob storage. All right, so we're right about an hour. We want to make sure we have some time for some Q&A here. Putting it all together, SharePoint service is a SaaS provider. This is great. We have a service out there. This is the guy that issues the token. Blobs is the storage that's backing that. The clients can now read and write directly to storage, and then I can auto that request via logs and metrics. Queues and blobs are useful for the bulk import and process scheduling. Again, you can use tables if you like. And Azcopy is a tool to simplify the import. Everything you need to do to get started with this is available online in a one-click install per language. So if you see here, we have the Visual Studio or Eclipse tooling, we have the libraries, we have the Core SDK. That Core SDK is a thing that has that storage emulator, that compute emulator, everything you need to do to get up and running. We have a whole bunch of different languages, Node, PHP, Java, things like that. So windowsazure.com. And then right here, there's a whole bunch of resources. The Azure Storage blog is a great resource for anyone using storage and also a way to ask questions in addition to the forums. We've been putting a lot of information there about best practice, about scalability, some of the new features in the storage clients, as well as, for example, the new Q10 networking improvements, things like that. And then there's great getting started online in the portal that'll give you code samples, how to get up and running really, really quickly. And then for the business decision makers in the room, there's a great interactive cost calculator and pricing details there. So you can go and kind of figure out, I need this much compute, I need this much storage, what's it going to cost? And then if you're just kind of getting new to storage and you have an appetite for some of the more in-depth scenarios and information, there's a build talk there from 2012, happened just a couple weeks ago, and you can really start talking about web scale applications and what it is to scale out. All right, questions? Anybody? All right, I'll be down here in front if you guys have any more questions. Other than that, it's been a good conference. I think there's just a couple more hours at the booth down there. So for any of the SharePoint-specific integration questions, there's a lot of SharePoint experts that would love to talk to you about this. This has been more the storage perspective. Yeah, hope you found this helpful, and yeah, have a good day.